So today we are going to be talking about the play Arcadia by Tom Stoppard. Arcadia is a wonderful play, and it has quite a bit of mathematics in it, which is a big risk that Stoppard took, but that he really carried off pretty successfully. And I have to say, the first time I saw Arcadia, being a mathematician myself, I really didn't get into it as much as I would have liked to, just because I was thinking of the first scene, what happened, what was the math behind it. And therefore, I think it's really useful to know a little bit about the things that Stoppard plays with. So we're going to go into the play and really look at some of the math behind the play. The first thing that Stoppard really does, and this is just a kind of tease almost, is he tells us about Fermat's last theorem. And if you haven't seen the play, Thomasina, who is one of the central characters of the play, is a math prodigy. And we are somewhere in the early 1800s. And Thomasina says something to the effect that she's familiar with Fermat's last theorem. And let me just tell you what this theorem says. We're all familiar with the Pythagorean theorem, which says that if you have a right-angled triangle, then the sum of the squares on the two sides, A and B, is equal to the square on the hypotenuse. So for example, in this triangle, you have one side that is 4, one side that is 3, and this side is 5, and you have this relationship. So a squared plus b squared equals c squared. That's the usual Pythagorean theorem. If you look at these numbers, there's not just one possible combination for a, b, and c. You can have 8, 15, and 17, 7, 24, and 25, and so on. In fact, there's an infinite number of such triples that satisfy this equation. What happens if I change that 2 into a 3, however? Supposing I now ask, are there 3 whole numbers, a, b, and c, such that a cubed plus b cubed equals c cubed? Turns out that there is no solution to this. You cannot find any 3 whole numbers for which this is true. Well, what happens if you put a 4 in there? It turns out that once again, you can't do that either. In fact, no matter what integer n you take, if n is greater than 2, there is no such solution for a, b, and c. And that is what Fermat wrote in the margin of his notebook. He wrote this theorem down that said that essentially you can only do it for 2, you can't do it for anything greater than 2. Now, Fermat used to write these things down, and often he had a proof, and sometimes he didn't. And in this case, what he wrote down in his margin was something very intriguing. He said that I have a truly ingenious proof for this result, but unfortunately, this margin is too small, and therefore I can't fit it in there. And of course, this became an unsolved problem for many years, for a few hundred years, and was finally solved in the 1990s. But Thomasina knows about this quote, and therefore she writes something in the, she says something in the play to the effect that, she's found this wonderful new mathematics, but the margin is too small, and she can't really fit it in there. So this is just a sort of amuse-bouche, if you like, and aperitif that Stoppard is giving us, because really the real part of the play, the real math, comes with the following. And this is something called the iterated algorithm. And this plays a really central role in the play. So let's see what an iterated algorithm is. This is something that the young Thomasina plays around with quite a bit. And it's something that the present-day mathematician, Valentine, also is involved with. And this is something that gives rise to all sorts of wonderfully colorful mathematics like fractals and so on, which we shall see in a minute. Let me give you the following. Let me give you 2 squares like this, and let me give you the following rule. I want to reproduce 3 copies of this pattern on the left in the box on the right. By that, I simply mean the following. Take that square and reproduce it 1, 2, and 3 in this order in the box on the right. So I've just copied this square 3 times in this square on the right. Now what I do is, an iterated algorithm, what it does is, it essentially has an input, which was this square, and an output, which was these 3 squares. What I'm going to do is I'm going to take this output and make it my new input. So that's what I'm doing. I've taken that output and made it my new input. And then I want to do the same operation again. Reproduce 3 copies of the pattern on the left in the box on the right. Well, what will that look like? If I perform that operation, I've just done the same thing 3 times. 1, 2, and 3. And again, I have the same thing. An input goes into an output. Well, we now want to choose this as our new input, and now repeat the same thing. And I keep doing this. And you will see that something really amazing happens, something completely unexpected. You will see a pattern emerge that is very complex. Even though this was a very simple rule, notice what's happening. Input goes to output. Now use that output as your new input, and that goes to your output. Notice what's happened. You've got this amazingly complex pattern, and of course you can keep repeating this over and over again. In fact, the idea is that you have to repeat it indefinitely, an infinite number of times. But what you've ended up with is what is called Sierpinski's triangle. And notice the complex form that this takes. We'll take a closer look at it in a minute. Notice what I've done on the right-hand side. I've simply taken the same triangle and made it an equilateral triangle, also twisted it around a little. This is an example of something called a fractal. And as I said, we'll take a closer look at it. This is from Wikipedia. Notice what's happening in this picture. The camera is basically zooming in into Sierpinski's triangle, and you notice 2 things. The first thing is that as you zoom in, it's the same figure again and again. You find that this is a self-similar figure. When you zoom in, you get the same picture, so that it's the, no matter how deep you go, you see the same picture. The second thing you'll notice is that most of this picture is really blank. I mean, there's not much in it. They're just holes all around. So it's not quite filled in. And that's one of the key properties of fractals. Because what you find is that a fractal has these 2 properties. The first property, as I said, was that blowing up a region shows a repetition of the same pattern. The second property is this idea that a fractal doesn't quite cover 2D space. It's not quite a line, so it's not like it's a 1D thing, and it's not a 2-dimensional object either. It's somewhere in between. So it has a dimension that's neither 1 nor 2. And in mathematics, you can actually see, as this slide shows, that the dimension is actually 1.585. So it's got this fractional dimension. Incidentally, this is a complete aside, but to get this a better idea of dimension, there's been a wonderful study of fractals related to the paintings of Jackson Pollock. A physicist, Richard Taylor of Australia, found that doing a fractal analysis of paintings by Pollock, and you can really see how these paintings have all these lines and everything in there, he found that Pollock actually had very fractal paintings. And what he found, moreover, was that, again, the amount of canvas covered and the lines that he had weren't quite 1-dimensional. They weren't simple lines, and they weren't quite 2-dimensional. They weren't completely filled in. So it had some sort of fractal dimension. And Taylor actually found that the dimension could go as high as 1.72. And he analyzed some paintings that were supposed to have been by Pollock, but it turned out they didn't quite match this. So he said that they weren't Pollock's. So this was a way of actually testing whether they were real or not. But subsequent analysis by Joan Smith said that this doesn't quite work, and you can't really rely on these results. So there's some controversy about that. But the main thing is that this gives you an idea of what fractals look like. They don't quite cover all of the space that you might expect. Now, one of the things in this wonderful play Arcadia, this is a line from that. Valentine talks about the things people write poetry about: clouds, daffodils, waterfalls. And this is in the context of the following. Since Thomasina is experimenting as a 17-year-old, she finds she kind of rails against traditional geometry, where everything is either straight lines or angles or curves. and it sort of ignores nature, a large part of nature. And what Valentine explains is that the kind of new geometry that Thomasina comes up with really is much better at describing something like clouds. Notice that when you really zoom into a cloud, you'll find that you once again get that self-similar structure. If you look at a coastline, you'll find that the edge of the coastline is very fractal, in the sense that if you zoom into this part, you'll find that there's similar gradations at a lower scale. If you look at something like a fern, you'll find that, okay, look at this whole fern, and then you will find that a part of the fern is the same picture repeated at a smaller level. Then if you look at each segment of this part, you'll find that that part is the same picture as this, and that's the same picture as the whole fern leaf. So this is, again, that self-similar nature. Snowflakes also have a fractal structure, and this is called Koch's snowflake, and this is a perfect pentagonal fractal. And of course, if you look at branching structures, that again shows that self-similarity. So what Thomasina was talking about was really trying to model all of these things which traditional geometry might not be able to. And another line from the play, Valentine talks about measles epidemics, rainfall averages, cotton prices. And sure enough, if you look at stock prices, for instance, you will find that when you take a part of it and blow it up, you find that the same gradations that are visible on the macroscopic scale also live on the microscopic scale. So if you measure how a stock changes by the minute, you'll find that it's the same picture, more or less, as the kinds of gradations you find, the kinds of changes you find when stock changes are measured over years, perhaps. And in fact, there is a reference to this which Valentine talks about, and that is when he's referring to the weather in the Sahara. That's a very slow change, whereas the weather in Manchester, let's say, is changing very rapidly. But if you look at the two climate patterns, the Sahara thing is simply the Manchester changes which have been stretched out. So it's just a matter of scale. I want to show you this on the next slide. And this is something, a fractal landscape generator. If you look at movies, some of the, maybe even the Star Wars movies, you will find that to make the landscape look good, look realistic, they actually use some sort of fractals in there. And the idea is that if you blow up a part of this, you'll find that the changes in the topography mirror the kinds of changes you find on a macroscopic scale. So fractals have been very useful in some sorts of image processing, in some sorts of realistic generation of landscapes of natural forms. So here is a quote directly from the play. Thomasina says that she has found a truly wonderful method whereby all forms of nature have to give up their numerical secrets. And she calls this the new geometry of irregular forms, which, as I said, she says that the margin of her notebook was not large enough for her to draw. So let's see what she could be talking about. What could Thomasina have really discovered? And one of the things that Thomasina says is that she wants to actually model an apple leaf. Now, if you look at an apple leaf, do you see any kind of self-similarity in it? Well, certainly you could say that the edge of the leaf has this very irregular structure. But more than that, I want you to concentrate on the veins that run through the leaves. And notice that the veins branch out, and then those branches have smaller branches as well. And so it is that same self-similar structure where if you take a little bit of a leaf and blow it up, you'll see the same branching structure that you see on a macroscopic level. So Thomasina wants to model this, but perhaps a better thing to model is a fern leaf, where you really see that self-similarity much more. So let's see how these fractal kinds of algorithms, these iterated algorithms, can actually model something like a fern leaf. And to get to that, I want to tell you how you make a fractal. I want to remind you again. We saw that one example with 3 squares. I want to do something a little more fancy. And what I'm going to use is a simple word that says Coke. So how do we make a fractal out of this? So the first step is to think of some sort of bounding image for this, a bounding area for this. And you can see a very simple answer would just be to fill this in with a black kind of thing, and you get a rectangle. So you have this rectangle on this side, and now I want to use small copies of this rectangle to cover the original image. So I take a small copy of this and put it over this piece. Then I put one over this piece. Then I'll put one over this piece, and so on. And what you can see is that there are actually 14 different pieces into which I can break this Coke word, and each piece basically can be covered by the rectangle. In some cases like this one, you would have to stretch the rectangle or make it oblique or something like that, but essentially that's the idea. You're taking the original shape, which was a rectangle, and then covering each piece of this by that same shape. So you're making this mapping. Just like in the first example, you just had 3 pieces of that mapping. So let's see how this works. So there's where I've covered everything. And now, step 3, I just iterate. I take this, and then each piece will be covered by an image Coke in the same way. And that's what the fractal will look like. If I keep iterating indefinitely, this is what I get. And you can actually see this in action in the following slide. And this actually is something that you can look up on this website. And what I'm going to do is go to words, and it already has that word Coke, and I'm just going to draw the word. And you see that actually forming before your eyes. And I can actually form a fractal of any word that I want. Let's say I want to form the name of the play. Well, I'll put in Arcadia, and there is the fractal version of Arcadia. Now, you might not be able to see it in the resolution, but each little line of this is Arcadia written along it, and then each little piece of that Arcadia again has Arcadia written in it. So, if you blow this up, you'll see Arcadia to the nth power. What about leaves or ferns? Well, if you look at a fern, here is the fern. What I'll do is I again need to cover this up by pieces, by blocks that bound this original fern. So first of all, I note that there is an original bounding box, which is this black piece over here, that completely covers the fern. Then I take that bounding box, and I take an image of it, and I cover this part of the fern. That's this black box here, which takes everything into account except for the first 2 leaves. It doesn't take this leaf, and it doesn't take this leaf into account. It takes the rest of the fern. I take an image of this and cover this. I have to stretch it out a little, but that's this piece here. I do the same with this piece. And then there's a tiny little green stalk, which I take a very thin image of this, shrunk up, and I cover that as well. So I use these 4 images, and then in the same way as before, I keep iterating. Input goes to output, goes to input, goes to output, and this is what I find. Let me show you how that looks. And we're going to see it form before our eyes. Let me show you that again. It happens so quickly that you can't really see it. Maybe this computer is too fast. On my home computer, it was working perfectly, but you can see that forming in front of you. So let's go on now and talk about something else, and that is how the iterated algorithms apply to Valentine's grouse problem. So what you saw, incidentally, was a picture of a grouse. I was talking to the cast members of the play, and they said that they'd never seen a grouse. So I was able to take a picture of Wikipedia and show it to them. Valentine has an interesting problem. He has about 200 years worth of grouse population shootings that have been recorded for him. So now, depending upon how many grouse there are, if there are more grouse, you will be able to shoot more of them. And so the indication of how many grouse were shot in a particular year actually tells you how large the population was in that year. And his problem is, given these populations, he wants to find an iterated algorithm that fits the data. So let's now explain this, and let's go back to the screen and see how these things work. Here is the idea that he's after. First of all, the population in any year will depend on the population from the year before. The more grouse there are in a certain year, the more grouse they will give birth to the next year. So the basic assumption in all of these population studies is that when you have population X in a certain year, then the next year you'll get population Y through some formula. That's the input, that's the output. Now, of course, what will happen is that the population Y that you have in the second year then becomes the population X for the next year. Then you get a new Y, then that goes back to X, then that goes back to Y, and so on. So you keep getting this input goes to output. And one of the key kinds of interesting questions that people ask is, what would happen if you keep iterating? How would the population end up? Where would it end up? Now, to go from X to Y, we need a mathematical formula. And a very simple formula is one where the population simply doubles every time period. What do I mean by time period? Well, for grouse, maybe, if you were claiming that the grouse doubled every time period, you'd probably be saying every year the grouse doubles. But if you have bacteria growing in a dish, then your time period might be much shorter. It might be every hour. So let's say that you have this model, and this actually is pretty accurate for many population growths. Say the initial population is 0.1 million. Then what you find is that each hour, this bacteria grows like this. And as you can see, this population is growing very fast. In fact, this is what is called exponential growth, where you just find that the population just zooms. Now, the question is this realistic? Will you actually have things that are going to be doubling each hour? And initially, that might happen, but eventually, you'll have a problem. Let's see what that problem is. So the question is it realistic? And these are my homemade special effects. This was actually a Coke glass, incidentally. But the idea is that you have limited space, you have limited food, and so you need a better model, because if this were actually doubling in this Petri dish, then the dish would explode. But the population that you get will be limited by the food and the space in this dish. So let's see what can be a better model. What I'm going to do is I'm going to change this right-hand side just a slight bit. What I'm going to do is I'm going to make this x goes to 2x times 1 minus x. And now notice what happens here. Remember, the population was 0.1 initially. Well, 1 minus 0.1 is 0.9, so that won't change much. But let's say x was close to 1. Let's say x was 0.99. This would be almost 0. So as x becomes closer to 1, this term becomes smaller and smaller, and it damps. It puts a damper on the whole population growth. As I said, it becomes smaller and puts the brakes on growth. So let's see how this works. There was the initial kind of evolution that we saw. And now I'm going to just see what happens when I add this extra term. Notice I start with the same population. The next year, instead of 0.2, it's 0.18. Not too bad. Then it's quite a bit different. And then it gets really different. And notice what happens. It kind of doesn't really go above 0.5. So this is what's happening to the population now, that initially it was blowing up. Now it's leveling off at 0.5. And this 0.5, incidentally, is what is called the carrying capacity of your Petri dish, or whatever your region is where you're looking at these objects, where you're looking at these grouse or your bacteria. So for the grouse, if you had a certain area that you were counting them, then this would be, you would say that the grouse have reached a steady state year after year. Their population is the same. This is what Valentine's problem is. That this is the kind of data that he has. He has the population over many years. So this is from 45 to 2005. This is the Maryland Chesapeake Bay blue crab harvest. So very similar to the grouse being shot. And what we find is that the population goes up and down. They've plotted the population for each year. It's not the population exactly, it's the harvest, similar to Valentine's thing. And what Valentine has to do is he has to find a formula for this. That's what his problem is. If you're given this, what is the formula that you should put on this side? Should it be x times 2x times 1 minus x or something else? Now, as he points out in the play, he's having a lot of problems actually trying to get this population. And the reason for that is that the data has a lot of noise. And let's see what we mean by noise. Think of the crab population in the Maryland Chesapeake Bay. From year to year, you might have variations that have nothing to do with the way things are reproducing, but have everything to do with weather. You might find that in a certain year, it's very cold, and so there are fewer crabs or more crabs, and then it's very hot, and so that affects the crabs. You might find that there's a lot of pollution, and that'll kill off a lot of crabs. You might find there's overfishing. So all of these things cause a real difference from year to year. And the hard part is to identify some sort of natural pattern that is hidden within these figures. There is some natural pattern, and then all of these factors are causing it to kind of go up and down. This noise is creating something more jerky. So what Valentine wants to do is actually find the actual rule disregarding noise. And the rule might be something very simple. It might be something like this, where the population just goes up and down each year. This kind of population is found quite often in actual natural populations. For instance, if you have a predator-prey relationship, you might have seen that certain years there are lots of birds. And the next year, the birds all die, and there might be a lot of insects. Then the birds feed on the insects, and then the next year, there'll be a lot of birds again. So that's the bird population. Or it might be something even more complicated, where you might find that there are 4 different population levels, and the population keeps oscillating between these 4 levels. So Valentine needs to find some sort of underlying rule like this. So let's see what we can do. Let's play around with this formula, and let's see if I can actually get this to work this time. This actually shows the same thing that we've been seeing, but here is the formula, 2 times x times 1 minus x. And what I'm going to do is I'm going to see what happens starting with an initial value of 0.1 and then taking 10 iterations. And you actually see the computer calculate all these iterations for you. And what that does is it gives you this kind of step which shows you that the iterations are getting closer and closer to 0.5, which is this value here. Let's see now what happens if I change this value. So what I'm going to do is I'm going to change this to 0.2, let's say. What happens now? Well, you find that once again, you're getting pretty close to 0.5. In fact, if you do 100 iterations, then you would find that you're still at that same level, but that's essentially trying to get to 0.5. And you find that no matter what initial condition you take, whether you take something very small, 0.0001, you find that, okay, once again, you end up at 0.5. Or if you take something very large, you'll end up at the same thing. So this shows that this formula always gives you the value 0.5 as your ending value, no matter what initial value you take. I want to show you one other thing, and that is what happens if you change this number here. Let's say I take 1.5 here. Then what will happen is that with 10 iterations, I'll find that I get to this point now, which is going to be 0.33, so basically 1/3. So changing this value always ends up giving you a final population, a limiting value of the intersection between this line and this curve. What we're going to do now is look at the same thing by a more graphical method that allows me to change things much, much easier. So let's do that now. This can actually be seen even better in this web applet, where I'm going to actually show you something called the nonlinear web. And that sounds very frightening, but it's actually the same thing we've been seeing right before. So what I'm going to do is, if you look at the bottom figures, you'll see that by changing that up and down, I actually can alter the figure that I have here, the number that I have here. And look at that now, 2 times x times 1 minus x. That's exactly the population growth model that we had a little while ago. What this does is it allows us to figure out how the population changes graphically. Notice that whether I start at this point or this point or this point or this point or whatever point, the final population always ends up at 0.5. So by this, what I see is that no matter what population we start with, the end result is always the same. So this is completely insensitive to the initial population. You know, if you look at the population over many years, what will happen, you'd say 2,000 years from now, it'll always end up at 0.5. So let's go back to that, and let's play around with it a little more. What happens if I change this? You know, let's say I take something like 1.5. You know, instead of 2, I've taken this to be 1.5. That's a smaller, that's a slower rate of growth. Well, now I find that the population ends up at this point, which is actually 1/3. That, again, you can read here, turns out to be 1/3. Again, no matter where I start, the population ends up at 1/3. And graphically, it's always going to be the intersection of this line and this curve. Let's change that, make it even smaller. Let's say I take it to be 0.5. What happens then? What do you think will happen? Well, let's try it. Let's say I start with a population here. That population comes down there. Then it goes even lower. So starting at any population now, what's happening? Population is going down to 0. So what we find is that in this case, since you have such a small value, the bacteria are being killed off. Half of them are being killed off every year. And so eventually, you'll find that the population goes down to 0. Changing this to something else, let's take 2.5. Well, now it's again going to be at that same point. This is what is called a fixed point. That's the stable population that you get. And you can see how the population changes graphically every year. Let's now go to something more interesting. Let's make this number higher. Let's say I take the number a little over 3. Notice what happens now. I'm going to delete the first few years of population change and show you what happens eventually. What happens eventually is that the population settles down into this routine. 1 year it's high, and that's 0.59. And then the next year it's low. I'm sorry. 1 year it's low, that's 0.59. The next year it's high, which is 0.74. It just keeps oscillating between these two values. And that was the picture that we saw, the boom and bust phenomenon. In fact, if you increase this a little more, you'll still see the same kind of pattern where you just have that same pattern, a periodic thing between two populations. Still the same pattern. Still the same pattern. Now see, something's changing. Now notice what's happened. Now you have 1, 2, 3, 4 populations. So this was the other picture that I showed you where it was changing between 4 different values. And you know, if you look at it more accurately, a more sensitive model, you'd be able to do it between even more values. So what we've seen is that this very simple formula involving just the terms x and 1 minus x can predict all sorts of different behavior. We saw the steady state behavior. We saw the case where things just die out. We saw the boom and bust phenomenon. And we saw even more complex periodic behavior. Now what I'm going to do is show you one more thing, and that is how this same population can give rise to chaos. And for that, I'm going to increase this over 3.5. So let's say I take 3.6 and see what I get now. Look at that. Now you get this very thick kind of pattern. And if you increase it even further, you start getting, you know, let's take it as high as it'll go. You start getting a complete mess. What does this mean? This means that you can't really predict where the population is going to end up. The population can be, it can end up at basically any value you want. And this is one of the things about chaos, is the unpredictability as to where the steady state, where the final population will end up. It won't end up in any fixed pattern. I want to show you one more thing about chaos, and let's go back to the screen, and this is an example of what happens with chaos. Notice what's happened here. I've taken two populations initially, the blue and the green, which are very close to each other. And what I find is, as I go in time, further in time, they really start to split apart. Whereas if you look here, they're really very far apart. Previously, I found that no matter where you started, it was completely insensitive to the initial value. Now, it's extremely sensitive to the initial value. And so chaos is characterized by this quality where the population becomes very sensitive to the initial value. And that's one of the reasons, that's one of the reasons why it's so difficult, in fact impossible, to predict weather in the long run. This is something from the play, which says that, Valentine talks about how the natural state of nature is chaotic, that the future is going to be disordered, things are unpredictable. And this is also characterized by the second law of thermodynamics in the play. Interestingly enough, what happens is that you can actually get to chaos from looking at populations, which is what Valentine was looking at. You can also get to chaos from looking at iterated algorithms, which are the basis of all of these things that Thomasina and Valentine were looking at. But in the play, Thomasina actually gets into chaos. She starts thinking about chaos through a very different way. She talks about the second law of thermodynamics. She makes an observation that this engine that they have in the garden, it'll never be able to really give you back all the energy that you put in. And Valentine later on, actually Septimus, her tutor, talks about a paper which happens to be by Fourier that talks about something similar occurring when heat is flowing through an object. So what is the second law of thermodynamics? Second law of thermodynamics basically states that the entropy of a closed system keeps increasing, and roughly speaking, that means that the usable energy that we have that makes things orderly in our universe, that allows me to sit here and be picturized by a computer, that keeps dissipating and turning into unusable energy. So the entropy is one sort of measure, roughly speaking, of the chaos in a system where, if energy had all dissipated, everything would be pretty much random and disorderly, so you wouldn't be able to harness things as you would expect ordinarily. So Thomasina observes this when she talks about the way that when you're dissolving jam in a cup, you can't really take it back. You can't work backwards. And the reason for that is that the heat equation essentially always moves forwards. When you break something, a window, there's some heat that gets dissipated as some energy that gets dissipated, and you can't really bring it back together. And this is brought out very nicely by Stoppard in the play, and I want to show you some of the ways that he does that. If you look at some of the things, the first thing is that if you look at the play, in the play there is this table with a bunch of props, and you keep seeing different props coming in over there, and so you get you're in some sense increasing the chaos on that table. This is the thing that I was talking about, ball breaking a window, jam not coming together again. It's really impossible to recover initial conditions because of this sensitivity, in the sense that if you try to work backwards, that becomes a problem that is extremely sensitive to where you start. So it's very difficult to recover initial conditions. And this is really, in some sense, what the play is talking about, what Stoppard is talking about, how difficult it is to figure out what happened in the past, just as it's very difficult to figure out what's going to happen in the future if you have a chaotic system. So there is this natural duality between trying to figure out how things evolve to the present state, and also how they will evolve from this state. And of course, what he does, what Stoppard does, is tie in all sorts of other things. Newtonism, where you had this idea that if you knew the equations of the universe, you could then plot out everything to the nearest, nearest whatever, very accurately. And that, of course, was in some sense repudiated by chaotic systems, where you really can't do that because you can never measure things exactly. So that's one thing he plays with. He plays with classicism, and he plays with new types of ideas in garden design and romanticism. So there are lots of things going on. I want to leave you with one final thought and one final visual in this, something called the Coverley set, which is something that Thomasina talks about. And again, these are quotes from the play where Valentine actually takes her algorithm, which is probably a very simple algorithm, and she's probably doing something like the first picture that I showed you, where she is taking three images, 3 copies of an image, and repeating. Remember, she only has pencil and paper, so she's unable to go very far in this generation. So she tries it a few times and has a vague idea of what's going on. She's on the verge, on the cusp of discovering something, but she doesn't quite make it in my mind. But if she had made it, then what would have happened? So what Valentine does is he takes her equations and programs it into a modern-day computer, and he generates something called the Coverley set. And this is where this quote comes from, of islands of order emerging from oceans of ashes. And this is really the terminology for fractals. So I want to show you one final thing. And I want to do it by this kind of equation. Very simple rule: x goes to x squared plus some constant, some number c. The only twist is that we're going to do it on the so-called complex plane. And if you're not familiar with that, it's no big deal. Just think of one dot being mapped to another dot on a plane, and it's given by this formula. What is c? Well, the number 0 is mapped to c. So c is some point on the plane, and 0 is mapped to c. Once again, we're going to do the input-output kind of thing, the iterated algorithm, where you start with an input and you get an output. Then you take that as your new input, and then you get another output. So that's your new output. Then you take that as your new input, and you get another output. So that's your new output. So we're going to do this, and one of several things will happen. What will happen is, if you start at the point 0, what might happen is that following this, you might keep going round and round in circles, maybe go to some point or end up in some fixed loop. Or it might happen that this point, this 0 point, might just keep going further and further and basically blow up, leave the page, go to infinity. So there are these two types of behavior. Incidentally, this kind of input-output generates something called the orbit of a point. So this is the orbit of the point. So the orbit of the point 0 will either go off to infinity or will stay finite. That's what I just was trying to explain. And what I want to do is I want to look at values of c for which the orbit of 0 will stay finite. You'll see two pictures in a minute. And on the left-hand side, those values of 0 for which the orbit says finite will be colored black. Finally, on the right-hand side, what you'll find is that the point 0 may have a finite orbit, in which case it will be colored black, as will be all other points which have a finite orbit. So some points will, when you start doing this input-output, they'll go off to infinity, whereas other points will remain inside. They'll remain finite. So those will be colored black. So here is what I'm going to show you finally, just to get in mind how this Julia set, how this Coverley set looks like. And what I want to do is I want to show you something very simple first. Here is something called the Mandelbrot set, and these are the values of c for which, when you look at this side, the value of the orbit of 0 remains finite. It remains pretty much in this picture. All of these points here have finite orbit. They keep going around finitely. Things over here are going off to infinity. Values of c around here make this point go off to infinity. I know that's a lot of information, so If you've seen this before, you've probably understood what I'm saying, but if not, just settle back and relax and try to think of Thomasina trying to generate these types of pictures, and her message basically coming through hundreds of years later in a present-day computer and giving us these pictures. So I'm going to go back to the pictures and show you what I mean. So what I'm going to do is I'm going to first of all take this point and show you what happens if I make this point go there. Notice what happens. So first of all, look at these points here. Look at these points. This is the orbit of 0. So you find that it's remaining finite. But as soon as I cross this boundary, the orbit of 0 blows up and goes out, and this whole thing disintegrates. For any point inside, as long as this white point is inside here, you'll find that this is a nice connected set. But as soon as I go outside, if I try to leave this, then this set breaks up into little pieces and becomes disconnected. So that's what's happening. Another thing that I can do is I think I can probably show you how this set changes if I make this zoom in. So what I'm going to do is I'm going to click on it, and notice what you'll see is that it's the same picture repeated. The big picture is repeated. It's the same picture. And this is, again, the whole idea about fractals. It's the same picture repeated again and again. And you can keep going on, just like the Sierpinski carpet, and you'll find that it's the same picture again and again. Incidentally, it happens over here too, where you find that if you blow up any part of this, you find that the boundary is extremely fractal, where it's got a number of kinks in it. And you can only describe it by very simple algorithms that are still pretty complicated. So I guess that brings together some of the ideas that are contained in this play, this wonderful play, I should say, Tom Stoppards' Arcadia. And I just want to thank you for listening to me. I'm Manil Suri, speaking from the University of Maryland, Baltimore County, and we have a sort of closing segment. Thank you.